All right, thank you very much. As you said, I'm Nick Farese. I'm a master's student from SUNY Brockport. My project focuses on determining the diet of lake trout from Otsego Lake using stomach contents, biochemical, and isotopic tracers. So normally this is the part of the presentation where I have to orient everybody to where Otsego Lake is because nobody ever knows where it is. But conveniently today I can point you to the window. Otsego Lake, for those that are Finger Lakes oriented, is about the same size as Canisius. It's just a bit deeper. It's about 7.8 miles long with an average depth of 162 feet and a max depth of 162 feet and an average depth of 82 feet. Otsego Lake is managed primarily for the proliferation of lake trout, with stocking dating back to the 1950s, with current stockings averaging about 2,500 yearlings annually. But despite these stockings, wild fish still dominate the population. Adults in the lake generally fall into two size categories. We have our smaller adults, which are much more common, which can be 500 to 700 millimeters, and our much larger adults, which can be greater than 900 millimeters. But we're missing the age classes, the size classes both in between these fish and between these fish. It is under the assumption that these fish are consumed almost immediately upon stocking. So Otsego Lake, like many of New York's waters, has had a long history of introduced and invasive species with records dating back to 1925. This list I'm going to go through is by no means a comprehensive list, but it's just the important ones for this, I'd like to focus on for this talk. As I move through, this dotted line here is the lake trout catch per net over time, with records dating back to 1935. So sometime between 1925 and 1942, cisco were accidentally stocked into the lake instead of the native lake whitefish. Then this was followed by the introduction of rainbow smelt in 1979, which were illegally stocked into the lake, and then alewife in 1986, which were believed to have been introduced by fishermen releasing their bait fish. Once alewife populations had reached their explosive capacity, as they often do, walleye stocking began in 1998 to try to control their population. And this, in combination with the introduction of the zebra mussel in 2007, are believed to have been what has caused the crash of the alewife population by 2012. So as we can see, as we move over this time period, the different planktivores become more dominant, starting with cisco, which were replaced by rainbow smelt, which were replaced by alewife. And throughout this time period, we can see a big change in the lake trout catch over time. So I like to separate Otsego Lake into three distinct time periods. We have the period before alewife, we have the period during alewife, and we have a period after alewife. And there's two main diet studies that were performed on Otsego Lake for lake trout. One performed in 1984 previous to alewife, and one performed in 2003 during alewife, but we're missing this after alewife period. So the diet before alewife were introduced is mainly the usual suspects. We had mainly slimy sculpin and chironomids, with lake trout, cisco, and yellow perch each being found in one stomach each. During alewife, unsurprisingly, lake trout, being the opportunistic feeders that they are, switched to eating almost entirely alewife, with 78.9% of the diet being alewife, 2.1% being chironomids, with slimy sculpin falling down to being only found in one stomach, along with creek chub and largemouth bass. So we know the before diet, we know the during diet. So the objective of this study is to determine the after diet using three analyses: stomach contents, fatty acids, and stable isotopes. The reason why we're using three different analyses is that each analysis comes with its own costs and benefits. One major one being that they reflect different periods of time. Stomach contents reflects a period of about a day. Fatty acids reflects a period of about a few weeks to a couple months. And stable isotopes is the longest, with several months being reflected on average. And using three different analyses can give us a more holistic image of what the lake trout are eating, because they kind of cover each other's bases with the pros and the cons. Moving into my methods, lake trout were collected using trap nets and gill nets during the fall of 2021 and 2022. Possible prey fishes were collected using boat and backpack electrofishing during the fall of 2021, the spring, summer, and fall of 2022, and the spring of 2023. And these fishes were limited to those of consumable size by lake trout because we wanted our isotopic and fatty acid signatures to be consistent with what the lake trout would eat in the wild. Due to the possibility of consumption of stocked lake trout, a subsample of stocked fish were taken off the hatchery truck previous to their release during the spring of 2022 and 2023. And then macroinvertebrates were sampled using Ekman sediment samplers during the spring, summer, and fall of 2022 and the spring of 2023, and this occurred in concert with crayfish collections. 3 different parts were taken from each lake trout. We took stomachs for stomach content analysis, dorsal muscle for stable isotope analyses, and a sample of belly flap for fatty acid analysis, with the latter 2 tissues being the most reflective of their respective analyses. Prey fishes were collected whole under the assumption that they would be consumed whole in the wild, and macroinvertebrates were aggregated by lowest taxonomic level possible by season when possible, so that we could reach our sample minimums. Stomach contents were identified to the lowest taxonomic level possible, and prey contribution was determined using wet weight and frequency of occurrence. Stable isotope samples were prepared at SUNY Brockport and sent to University of California, Davis for carbon-13 and nitrogen-15 analysis using an elemental analyzer with a mass spectrometer. And lipids were measured gravimetrically, and fatty acids were quantified using a gas chromatograph mass spectrometer. Moving into my results, 36 of the 59 lake trout that we collected had some stomach contents. We can see that they had a good variety of macroinvertebrates in the stomach, as well as several fishes, as well as some lake trout eggs in the diet. Obviously, these are fall samples, so this is going to be a seasonal contribution to their lake trout diet. But if we look at the different quantifications of these metrics, we can see kind of a discrepancy, and that's a difference of how often the prey shows up versus how heavy the prey is within the stomach. And this is mainly shown by 2 of the main contributions for each analysis. Starting off with chironomids, which were found in almost 60% of the stomachs that had contents, but were in relatively low weight, whereas rock bass was 45% of the diet by wet weight, but was only 1 fish in 1 stomach. It just happened to be a very large rock bass. So what we did was we kind of took both of these metrics into account, and we came up with slimy sculpin, chironomids, and dracenids being the most likely greatest contribution to the lake trout diet via stomach contents. Moving into stable isotopes, carbon-13 is a metric of your carbon pathway, so that those in the same horizontal space generally are getting their carbon from the same source. Whereas nitrogen-15 is indicative of trophic level. So as we move from the bottom to the top, we're moving up trophic levels, which makes sense because we have our macroinvertebrates down here, our prey fishes in the center, and our lake trout at the top. And as I move through the next few slides, I would like to point out that the species that are pictured are a subsample of the species that we collected. All of these graphs look very messy when I include all of them. We looked at 36 different species, including a variety of macroinvertebrates and prey fishes within Otsego's watershed, Otsego Lake itself. So to determine the contribution of each of these prey fish to the lake trout diet, we used Bayesian 2-source isotope mixing models in the MixR package of R to really look at how much each of these contributes to the lake trout diet on average. This analysis was performed at 3 million permutations with all Gell-Mann statistics falling below 1.05, and all these numbers mean is that the prey fish were well represented within the models. And this chart to the right is indicative of how many of each percent contribution was determined throughout those 3 million permutations. So that the center of this peak is the most likely contribution for that species. And what we're really shooting for is these more narrow peaks so that we can say with relative certainty that the contribution is somewhere between these two end goals. So we did get some pretty nice peaks this time, and we found that rainbow smelt are contributing 61% of the diet, slimy sculpin 16, and dracenids 9.4 on average. Moving into the fatty acid analysis, applicably enough, fatty acid analysis operates under the assumption that you are what you eat, so that the fatty acids of the prey are passed up the food chain to the predator. So if you look at the fatty acids of the prey, you'll see them reflected into the predator. And each one of these points on this graph represents one individual fish's fatty acid signature. And that's the combination of all 25 different fatty acids that we looked at for this project. And we can see that the different species generally clump within their species. So that we have our Centrarchidae plotting over here, a walleye in the center, a big chunk of yellow perch, our slimy sculpin at the bottom, and our rainbow smelt over to the left. And these are separated by three main fatty acids. Our 16, 1, and 7 dictates the vertical space so that it's distinguishing these different species from one another in a vertical separation, whereas the left to right is separated by 25 and 3 and 22, 6, and 3. And using Permanova, we determined that there was a significant difference between the different prey species, which is a requirement of using fatty acid signature analysis. So because we met that requirement, we can move on to the dietary estimates. And we used the QFASR package within R to determine qualitative fatty acid signatures for the different prey. And we found that slimy sculpin contributed the most of the diet with 45.8% of the diet, bluegill at 20.9% of the diet, and dracenids at 19.2%, with rainbow smelt falling down to 14.1% relative to their stable isotope results. So moving through the results throughout time, we can kind of see that the diet of lake trout has shifted over time. We saw our pre-alewife diet consisting mainly of slimy sculpin and chironomids. Our during alewife time diet being reflected as alewife and chironomids, and our post-alewife time being reflected as slimy sculpin, rainbow smelt, dracenids, and chironomids. And I have a lot of people to thank for this project. It really was a collaborative effort. I'd like to thank Brockport students for their help during analyses, faculty, staff, and students from SUNY's Cobleskill and Oneonta for their help, as well as Region 4 New York State DEC's Region 4 Fisheries for their time and effort during sample collections, as well as my various funding sources. And with that, I would thank you very much for listening.
Hey Nick, do you think that lake trout are actually consuming dracenids, or do you think that there's a high catch of maybe them eating some other prey